I'm going to talk about what's known as the most beautiful equation, published in 1748 by Leonhard Euler. It's known as Euler's identity. But first, we have to review some basic Taylor series. We know that cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and etc. Sine of x equals x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial, etc. And we know that e to the x equals 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, etc. Now, what if we threw in an I, that is the square root of -1? If we substitute ix into wherever we see x in the previous equation, we get this following Taylor series: 1 plus ix minus x squared over 2 factorial minus ix to the 3rd over 3 factorial plus x to the 4th over 4 factorial, and etc. And as you can see, there's some alternating real terms and some imaginary terms. And if we separate the real terms and the imaginary terms, we get the following equation. Now, this is the cool part. If you realize that this first part, the real part, is cosine, and this secondary part, the imaginary part, is the same thing as the sine Taylor series, we can write e to the ix as cosine of x plus I times sine of x. What if you plug pi into this equation? We get cosine of pi is -1, and we all know that sine of pi equals 0. Hence, e to the pi I is really just -1, which is Euler's famous identity. And this is the way Euler came up with this solution, but I want to show another way that we can look at this. One of the defining properties of the function e to the x is that its derivative is itself. Here, the slope at 0 is e to the 0, or 1. The slope at 1 is e to the 1, or e. Similarly, the derivative of e to the 2x is 2 times e to the 2x, which is the function multiplied by the factor in the exponent. So, if we write this in terms of vectors, we have the position vector is the same as the velocity vector for e to the x. But for e to the 2x, the velocity vector is twice the size of the position vector. So what happens if this factor happens to be I? So for e to the ix, this I factor has the effect of rotating the velocity vector, as you can see here. And if you think of it in the imaginary plane, as time goes on, this circle is created, something like this. This is what the actual function of e to the ix looks like. Now if we shrink this down into 2 dimensions, we get the following picture. As we increase time, set t equal to pi, we realize that the function gives us -1. So this is just another graphical representation of how e to the I pi equals -1. And if you move this -1 over, you realize that this equation uses 5 of the coolest, most basic values in math, which is just simply amazing. All I have to say is wow.